Alright, in this video I'm going to be working BC Homework 3.1. And so we're going to be using the first derivative to determine things like where a function's increasing, decreasing, and maybe where it's got maxima or minima, and maybe some other stuff too. Alright, so here's an equation for f prime, determine where f is increasing or decreasing. Okay, so we're going to, since we're already starting with f prime, we're going to want to make either a sketch of the graph or a sign chart. Okay, and for a, it's f of x equals x plus 5. That's only got 1, 0 at x equals negative 5. It's a line with positive slope, so I know that the graph more or less looks like that. It wasn't the best drawing. I probably should have drawn the line before the x-intercept, but that's fine. I can see that to the left of x equals negative 5, f prime is going to be negative. This is a sketch of f prime. Okay, so let's say decreasing when x is less than negative 5, and increasing when x is greater than negative 5. Okay, and that's because, when x is greater than negative 5, f prime is positive. Now, b is f prime equals x minus x squared, so we're going to have to do some factoring on that. So I'm going to factor out the x and have x times 1 minus x. And I know that x squared, or x minus x squared, is a second degree polynomial with a negative leading coefficient, so its graph is going to kind of look like that. And I see from the factored form it's got two different zeros. It's going to be x equals 0 and x equals 1. And so that's a sketch of the graph, and I could say, all right, well, f is going to be decreasing where its derivative is negative. This is a sketch of its derivative. So that's going to be when x is less than 0 and when x is greater than 1. And f would be increasing where its derivative is positive over here, where x is between 0 and 1. Alright, so while a and b were both polynomials, c is a fraction, and I'm not as confident in my ability to sketch, the graph of this function. So I'm going to just say, okay, f prime of x equals x over x minus 3. I'm going to make a sign chart. I think that's why I put that one on there. So to kind of force myself to, I can use a sign chart if I have to. So the zeros of the numerator and the denominator are both important numbers, I think is what I called them. I might have called them critical numbers. I think I called them key numbers last year in pre-cal. Key numbers that we need to put on our sign charts were 0 and 3. I think I avoided that. I didn't want to call them critical numbers because reasons you know now. And so I'm going to choose a test point, something between 0 and 3, like x equals 1. Okay, f prime of 1 is going to equal 1 over 1 minus 3. That's a negative number. Okay, so I just put in a negative there. Choose something bigger than 3, like x equals, you could do 4, but I like to do something like nice and clear of it so that you kind of get the point. So 10 over 7, that's definitely a positive number. And then, all right, with x equaling something negative, like negative 2, doesn't matter, any negative number you want. We're going to plug that in. I'm going to get negative 2 over negative 2 minus 3 more, and so that's going to also be positive. All right, so now if I want to know where the function's decreasing, that's where it's got a negative derivative. That's on the interval 0 to 3. Okay, and you can write a closed interval and an open interval. We discussed that in class. You can write with interval notation. There's an inequality. It does not matter. For increasing, it's where the derivative is positive. And I'll say that's from negative infinity up to 0, also 3 to infinity. All right, now D is, it can go either way on this one. If you know that e to the x is always positive, then you can just say, okay, it's just multiplying x plus 4 by a positive number, so it's going to be somehow curved, but it's going to overall kind of just look like y equals x plus 4, and you could draw the graph kind of similar to the way we drew it on A. But otherwise, you could just kind of draw right here and say, okay, well, key number is going to be negative 4. It's actually the only critical point of f. If you think about the places where f prime is 0 or undefined, Actually, going back to C, x equals 0 and x equals 3, those were critical numbers of f. Okay, but that's a different discussion. So x equals -4, I'm just going to do the sign chart thing. Just go to the left, go to the right. E to the x can never equal 0, though, because if you try to set e to the x equals 0, take the log of both sides, you're trying to take the log of 0, it's like, oh yeah, that doesn't exist. Think about it, maybe x equals -5. F prime of -5 equals -5 plus 4, -1 e to the -5. E to the -5 is a positive number, so that's negative. And then to the right, like x equals +5, f prime of +5 equals 5 plus 4 is 9, e to the +5, and that's a very positive number. Okay, so there we go. Seeing decreasing with a negative derivative, x is less than 4. Increasing with a positive derivative over here, where x is greater than -4. All right, with e, we're back to the realm of polynomials, so it's already factored for us. Okay, I'm going to sketch the graph of this because I can tell this is going to be a third-degree polynomial because of the 1 power of x plus the 2 more powers of x multiplied there. The leading coefficient is going to be 1. I'm envisioning if I was to square that x minus 3 or multiply x minus 3 times x minus 3, it would be x squared minus 6x plus 9. I could distribute that x over. See what's going to happen. It's going to be a positive x to the third. But because of that x minus 3 squared, it's going to have a double root, so it's going to bounce where x equals 3. So the roots are going to be 0 and 3, and x equals 3 will be a double root. So draw that, and then label, okay, that's 0, and this is 3. Right, and because it has a positive leading coefficient, that's how I knew it was coming from below and eventually going up. And if you just wanted to say, okay, I can see that the critical points are 0 and 3, and I'll make a sign chart, you end up with the same information, just maybe a little bit slower, maybe a little bit more computation. Okay, so x times x minus 3 squared, decreasing is where we have a negative derivative. That would be where x is less than 0, and increasing is where we have a positive derivative. And yeah, it is definitely okay to just say right here x is greater than 0. That's fine. It's not a big deal. We don't have to worry about that place where x equals 3. Nobody's going to be telling you you're wrong based on your answer about what's happening to the graph of f at x equals 3, unless they ask you about whether it's the location of a maximum, a minimum, or neither. But that's not the question at hand here. It's about increase and decrease. All right, now the last one I've got f. This is another polynomial. Oh, and I'm going to do this one a different way. I forgot about this, but it would work really well for this one. So what we need to do is identify the critical points of f, and that -2, that's going to impact the leading coefficient of f prime, but that's not going to impact the degree or any of the zeros, right? It's not contributing any zeros. Zeros are going to be -6 and -1. I'll put these here. And what we're going to do is we're just going to do one test point, and then we're going to use the multiplicity of the roots to determine whether or not there's going to be a sign change. I'd forgotten about this trick, but one of my students had reminded me of it, and I really liked that. So I'm going to do that one here. So I'm going to say where x equals 0, I've got f prime of 0 equaling -2 times 1 to the third times 6 to the fourth. That's a big negative number. Okay, over there. And then I know that at -1, that is a triple root, so it's an odd multiplicity root. There is going to be a sign change at x equals -6. That's a quadruple root, and even multiplicity is no sign change. Yeah, that kind of makes sense. We've got a 7th degree polynomial. Looks like it's coming from above and eventually going down. Okay, decreasing intervals where the derivative is negative, and increasing on intervals where the derivative is positive, so say x is less than -1. Right, I really like those where they, give you the derivative already and then, have you do the sign chart analysis or whatever. But there are also problems like this where we have to start out by taking the derivative ourselves and then do the analysis. So we're going to determine the intervals on which this function is increasing and decreasing, but first we're going to take the derivative. Okay, so we're going to probably, use all of our different rules. Power, product, quotient, chain. All right, so for the first one, f prime of x is going to equal 2x minus 2. And we're going to need to know where this thing is positive and negative. So 2x minus 2, thinking about where that would equal 0, that would be where x equals 1. It's a line with a positive slope, or you could make a sign chart if you wanted, or you could just sketch the graph the old-fashioned way, 2x minus 2, and, on a grid or something, and get all the same information. It's going to be increasing down here this time when x is greater than 1, and it'll be decreasing when x is less than 1 because of the negative first derivative. All right, for b, if f of x equals x e to the x, I'm going to need to use the product rule to take the derivative. So first I'm going to take the derivative of x, and that's 1, leave e to the x the same, then I'll add, leaving x the same, taking the derivative of e to the x, which is just e to the x. Okay, now if I want to make a sign chart on this, I need to have it factored, but I do see that there's an e to the x common to both terms in this sum here, so I'm going to factor out the e to the x and be left with a 1 plus x. Okay, so, the critical number on my sign chart would be x equals negative 1. Okay, because e to the x is never going to equal 0. We kind of already talked about that one in this one. So, when x is greater than negative 1, say x equals 0. F prime of 0 is going to equal e to the 0 is 1 times 1 plus 0 is also 1. And we've got a positive number. F prime of negative 2 would equal e to the negative 2 times negative 2 plus 1. That's going to be negative. There we go. All right, so increasing is where we've got a positive first derivative. X is greater than negative 1. Decreasing where there's a negative first derivative, and that is when x is less than negative 1. Okay, C, this one's going to require a quotient rule, and this is really the nice thing about calculus, is that regardless of how you're doing with the derivative rules, whether you've just totally mastered them at this point or you're still on your way to getting there, you're still going to get plenty of practice at each step along the way. So it's if you don't give up, we're just going to keep building up those skills, and slow and steady is going to win the race here. So we're going to need to take the derivative, and it's going to be using the quotient rule. Starts with bottom times the derivative of the top minus the top. Times the derivative of the bottom divided by the bottom squared. Okay, I remember there being something I think this works out nice, so I'm just gonna have faith in this one, because you need a couple of problems like this along the way too. So we're going to expand the numerator, and I'm probably just going to end up replacing that. So 2x squared plus 2x right there minus 2x. Okay, minus 2, that's interesting. Oh, okay, yeah, that does make sense, though, because that's 2 times x minus 1. Okay, I probably could have done that a little easier. Minus an x squared plus a 2x and minus a 1. Yeah, I think I'm going to use that as a placeholder and then get rid of a bunch of this stuff. Rewrite the numerator. Okay, so 2x squared minus x squared is going to be 1x squared. Okay, 2x's were canceling out, but then I still have this plus 2x. And then minus 2 and minus 1 is minus 3. And yeah, sure enough, that's going to be factorable. Yeah, I thought there was going to be some sort of payoff to this one. All right, I'm going to factor that numerator. Two numbers that multiply to negative 3 while adding to positive 2. That must be x plus 3x minus 1. Okay, so we've got 4 critical numbers. Lots of excitement on this one. And let's zoom out, give us a little more room. Number line going. I'm going to have negative 3, negative 1, which is a double root. Okay, so I guess there's 3 critical numbers. Okay, so I'll start with x equals 0. I'm going to have positive, negative, divided by positive. Okay, because anything squared is going to be positive, so that would be negative x equals 2, positive, positive, positive. Right, x equals negative 2. Yeah, that makes sense. We would not see a sign change over that double root, even though it is in the denominator. We just see the vertical asymptotes pieces sitting together there. Okay, and then the last one, we should see a sign change. Maybe x equals negative 4. That would be negative, negative, divided by positive. Yeah, sure enough, there we go. All right, increasing positive first derivative. Infinity up to negative 3 and positive 1 to positive infinity. Decreasing, you could say negative 3 to negative 1 and negative 1 to 1, as open intervals, x being sure to exclude that x equals negative 1. That would probably actually make a lot of sense since that was not part of the domain. Maybe I'll do that too. And that would probably be the most accurate statement of the intervals on which this function is increasing and decreasing. Alright, this last one is going to have chain rule. So on the outside, I've got the natural log, and on the inside, I've got x squared plus 1. And so, because this is, mostly a derivative rules practice review, worked inside of the new thing, I figured I'd do those nice. Alright, so f prime of x will equal 1 over whatever went on the inside of the natural log, x squared plus 1 multiplied by 2x to the chain. But I will write that as one fraction so I can kind of do the analysis that I need to. Okay, so 2x over x squared plus 1. When I go to make my sign chart, I'm going to make a sign chart because it's a fraction. I don't really consider myself very good at just visualizing the graphs of those. I'm going to put down the critical numbers, and that would be any place where the numerator or the denominator of this fraction is equal to 0. Okay, well, the numerator could equal 0 at x equals 0, but the denominator is not ever going to equal 0 for any real value of x. So I just put x equals 0 down on my number line, choose a positive number, think, okay, 1. 2 times 1 over 1 squared plus 1, that's definitely positive. And choose a number less than 0, like negative 1. 2 times negative 1, okay, it's going to be negative in the numerator, positive in the denominator. There we go. All right, increasing is where f prime of x is greater than 0. So that would be like 0 to infinity. And decreasing where f prime of x is less than 0. And I can say that was negative infinity up to 0. Alright, now the next one is find the critical points, determine if it's maximum, minimum, neither, justify your answer. Alright, so f prime of x equals 1 minus x. So, okay, that would equal 0 when x equals 1. 1 minus x is a line with negative slope. So draw it like that. And say, okay, well, right here, f prime went from positive to negative. So I'm going to say x equals 1 is a local maximum. Okay, and reason being f prime went from positive to negative. Okay, and our answer does need to be pretty much something to that effect. Okay, you don't have to use all words. You can use symbols, but you do need to express that it was the sign change from positive to negative in the first derivative of f that's what's causing the local maximum at x equals 1. For b, we've got a factored polynomial, so 1 minus x and x minus 3. Now, if we were to multiply that out, and maybe I will, I'm going to say, okay, the zeros of this are pretty clearly 1 and 3. Okay, but if I was to multiply that out, I'd get negative x squared, okay, positive 1x, positive 3x, so plus 4x. You don't really need to see anything else. I guess minus 3, because the leading term is negative x squared, so it's going to be a downward facing parabola is what I'm saying. And so I'm going to say, right, this is going to be, who knows if it's going to, well, looks good enough. Okay, that's my parabola for f prime, and we'll say, all right. And local maximum would be where the derivative went from positive to negative, so x equals 3. F prime went from positive to negative. Okay, and then x equals 1, that's the other critical point, the other place where f prime equals 0. Okay, that's going to be a minimum, because f prime went from negative to positive. Okay, f went from decreasing to increasing. Okay, oh, this next one, I like this one. This is maybe the type of function you might not have thought about since maybe like algebra 2. But y equals x minus 4 squared in parentheses with no other factors. That's just going to be a parabola that's shifted right by 4. So it's going to look a lot like that. Okay, I'm sure. Right there at 4, and where it's just touching the axis. Right, so I would say x equals 4 is a critical point right there. We're seeing f prime is equaling 0. So say x equals 4 is the location of a critical point, but it's going to be neither a maximum or a minimum. And my reason is going to be f prime did not change signs. Maybe I would actually say does not change signs. I don't need to say does not change sign at x equals 4 because I've just, already clearly stated I'm talking about what's happening at x equals 4 already. All right, in D we've got 3 factors and they're all distinct, and this would make a third degree polynomial with a positive leading coefficient. I'll draw it so that there's 3 different roots. X equals 0, x equals 3, x equals 6. All right, so thinking about a maximum, that's going to be a place where the derivative goes from positive to negative. That would be right there. That's x equals 3. And the other 2 are both going to be local minima because f prime is going from negative to positive. All right, so x equals 0 and x equals 6 are both the location of relative minima. And my reason is f prime went from negative to positive. Okay, this one's a little different. F prime of x equals 3 minus square root of x. And I don't know about you, I feel like I can probably sketch the graph of this if I just really think about it hard, but what I would rather do is just make a sign chart. So on ones where it's not totally obvious, we're just going to think about, if possible, and I think we can on this, what value of x would make f prime equal to 0? And that would be x equals 9. Okay, the domain of this thing x is going to need to be greater than or equal to 0, but, we're not going to have to worry about any other place where we're taking the square root of a negative number because that's not part of this class. So we'll just say, okay, our key number on our sign chart is going to be x equals 9. And then now that I think about it, okay, if I take, a big number bigger than 9, but that I might like to take the square root of, like, I don't know, say x equals 16, f prime is going to equal 3 minus 4, that's a negative number. And x equals, say, maybe 4, a number less than 9 that I might like to take the square root of, f prime will equal 3 minus 2, which is a positive number. And so since f prime is going from positive to negative, I'm going to say x equals 9 is the location of a maximum. Oh, and then for f prime of x equals natural log x. Okay, so on one hand, if you know that the graph of y equals log x looks like that, let's see, okay, that's at x equals 1, and there's actually that vertical asymptote at x equals 0, but that's not as important as the fact that, okay, that's fine, only 0, and it's a sign change from negative to positive, so it's going to be a local minimum. But if you didn't just know that graph like that, what would you do? Okay, you would want to make a sign chart. And maybe you're thinking, okay, well, where does log x equals here? And you're not totally sure. Okay, well, you're just going to set up an equation, natural log x equals 0, and you're going to solve it. Because you know how to solve this equation. You're going to take e to both sides power, so e to the natural log x. That's going to be x equals e to the 0. And I know you know what e to the 0 is. That's going to be x equals 1. We go over here, say 1, and it's like, oh goodness, okay, I know that like 0 is the vertical asymptote on the log, and so it's like, what's going to happen here? So, number bigger than 1, like maybe, I don't know, e, and x equals e, f prime is going to equal the natural log of e. The exponent I put on e to get e, that's going to equal 1. And then a number, so that's positive, that's what I'm saying. And then a number that's between 0 and 1, you could say 1 over e. And then f prime is the natural log of 1 over e. The exponent I put on e to get 1 over e, that's going to be a negative 1 exponent. It's a negative number. And then you'd see the same thing. F prime went from negative to positive at that spot. That one's tricky, but still definitely one that we want to think about. All right, now number 4 is kind of more of the same, but we're going to have to take the derivative first. And, this first 4 problems, this has been kind of a grind, but I will say that I think that this is really important, as a first-time calculus student, that you go through and work problems like these algebraically and looking at pictures of graphs and looking at tables and stuff. And I feel like maybe the repetitive algebraic ones had been something that had been missing from my class for a while. So I think it's definitely important that we're doing those here today. We're going to start with finding critical points, so that's going to start with taking a derivative. We need to keep sharpening those derivative taking skills. So that's going to be 6x to the 2, 6x to the 1, and negative 12. We're going to need to factor that. X plus 2 and x minus 1. I've got it factored up. I'm going to make a sketch of the graph. This is a second-degree polynomial with a positive leading coefficient. I know that didn't snap to. Hold on. What's going on here? There we go. That's not as good as I'd hoped for, but it'll work. Okay, it's supposed to be a narrow parabola, but I guess that's up to your idea of the scale. And the zeros are going to be x equals negative 2 and x equals positive 1. So it's the sketch of f prime. And so if we're thinking about a maximum, that's where the derivative goes from positive to negative, and that's x equals negative 2. And Then for a minimum, that would be when the derivative goes from negative to positive. That would be x equals positive 1. Right. Now, see, I felt like there was something else I was going to say about this one, but no, okay, I'm just going to move on to B, and I'll clear out both of them at the same time. Okay, so 12 cube root x, that's 12x to the 1/3. So f prime of x is going to equal the derivative of x plus 1/3 of 12x to the negative 2/3. Oh, yeah, these ones with the cube root, these can be tricky. Okay, so we just got to be careful for these. F prime could equal 0, or f prime could be undefined, and both of those are going to be outcomes we need to be aware of. F prime could equal 0 if, 4x to the negative 2/3 equaled negative 1. I could divide by by 4. Okay, maybe I will say that means x to the positive 2/3 equals negative 4. I'm going to say that doesn't seem possible, because how would you take a number to the 2/3 power and get something that's negative? Let me think about that. Let's make sure I'm not missing anything. Yeah, that's not going to happen. Okay, no problem there. And then I don't have to worry about that anymore. But f prime could not exist because this is 4 over x to the 2/3 when x equals 0. So I'm going to think about it. X equals 0. What's going on with this thing? F prime, because 12 cube root x. Oh, we're having a vertical tangent on the graph of f at that spot. Yeah, okay. I think it's going to be neither a maximum nor a minimum, though. So yeah, because x to the 2/3 is going to be squaring the cube root of something, so we're squaring it, and it's going to be 1 plus 4 times a thing that's squared. So these will both be positive, and x equals 0 is neither. F prime had no sign change. For C, f equals x log x. So I'm going to take the derivative using the product rule. Derivative of x is 1. Need to leave natural log x the same. Then leave the x the same and take the derivative of the natural log. And so that's going to be, I'm going to write the 1 first so don't get confused with the argument of the log. So that's 1 plus log x. Okay, my critical point would be anywhere where f prime is undefined. Well, I've got the same domain issue on the derivative that I have on the original, which is not a surprise at all. I'm taking a log, and I'm not going to be able to do that when x is not positive, and so I'm not going to have a derivative when x is not positive either. And so I will say, all right, but this can equal 0. So 1 plus log x equals 0. Subtract 1. Take e to both sides power. Say, all right. Okay, well, 1 over e. That's my critical number. Okay, that's e is between 2 and 3, so this is like somewhere between half and a third. And okay, again, I've got this kind of edge in my domain. And so I need to think of something that's between 0 and 1 over e. I'd say 1 over e squared. Okay, I think that might be a good idea. And then also something bigger than 1 over e. I don't know, maybe e to the 10th. Okay, that might be a good idea. And so I'll think about f prime of both of these values. F prime of 1 over e to the 2. That's going to equal 1 plus the natural log of e to the negative 2. So that's 1 plus negative 2. And that'll be negative 1. That's a negative number. F prime of e to the 10 would be 1 plus the natural log of e to the 10. 11. That's a positive number. And I'm seeing that f prime went from negative to positive at x equals 1 over e. So I'm going to say that's a local minimum. All right. D, we're going to, I think this one maybe is going to have one that's a, yeah, I think it's going to have a neither or something. Okay, f prime of x will be 4x to the third minus 4x. Yeah. No, no, it's not. It's going to have 3. It's going to be very similar to one we did earlier. We might have done increase, decrease, increase or something, but on this one, but okay, we're going to factor it, factor the 4x out, be left with an x squared and a negative 1. Realize we can keep going. Sign chart or sketch the graph. This is a third degree polynomial, positive leading coefficient. I've got this. Okay, negative 1, 0, and 1. Right, and so if I want to know for a local maximum, I think we already did this. X equals 0. I think I may have thought this was going to have a double root in the first derivative, which is kind of what I wanted. X equals 0 maximum f prime went from positive to negative. I would think that I'd written that enough times that I could remember, but the other ones are going to be minima because the derivative is going from negative to positive. Okay, so this is a minimum because f prime went from negative to positive, and we are ready to move on. Okay, so the next one we're going to need to use the quotient rule. It's definitely good. We're getting our work in on that. So bottom derivative of the top minus top derivative of the bottom divided by bottom squared. So this actually won't be too bad. 2x squared minus 2x minus an x squared. Okay, we should be able to do that. Okay, so f prime of x is going to be equal to 1x squared minus 2x divided by x minus 1 squared. And I can factor this just a little bit more. Okay, let's see my critical numbers. I am hopeless to draw a graph of this thing, so I'm just going to label the zeros of both the numerator and the denominator, make a sign chart, and go from there. So I'm going to plug in negative 1, be negative over, okay, always going to be positive in the denominator because that's square, so it's going to be positive here, 0.5. I'm going to have positive negative, positive denominator, x equals 1.5. Let's see, positive is still negative. Yeah, okay, that's not going to change because that's only the denominator that's going to change when we go across x equals 1, so it's still negative. And I suspect when I go over 2, like to x equals 3, yeah, it's going to be positive, positive, positive. All right. So a critical point where the derivative went from positive to negative is going to be x equals 0. That's maximum. X equals 2 is going to be a local minimum. Okay, now I will say at x equals 1, I suppose you might could say that's a critical point of f, but I don't know that I would because x equals 1 is not even in the domain. I mean, it's definitely neither because f prime didn't change signs, but I'm going to say really my reason is that this isn't even like part of the function. So how could it be a maximum or a minimum if there's not even any function there? Right, and then f of x equals x minus 2 sine x. So I need to take the derivative. I'll get 1 minus 2 cosine x between 0 and 2 pi. All right, so I need to know where this thing equals 0. So maybe 1 equals 2 cosine x. That would be when cosine x was equaling 1/2. Okay, thinking about, where on the unit circle cosine would be positive 1/2. That would be over here, not very far over, right? Because 1/2 is the smaller leg of a 30, 60, 90 triangle. Okay, and I've got, right, in these places, x equals pi over 3 and x equals 5 pi over 3. So I'm going to kind of just mark off these pi over 3 and 5 pi over 3. I'm just going to do the same thing, like the same process I've been doing positive, negative, 0 analysis. But I'm going to, I don't know, maybe I'll start with pi over 5. I like pi over 4 for this one. I see how the computation is going to go. F prime of pi over 4 would be 1 minus 2 times the cosine of pi over 4. So 2 times root 2 over 2. So that's 1 minus the square root of 2. I need you to be able to think about this and know whether this is positive or negative. Square root of 2, that's got to be a number that's bigger than 1, right? It wouldn't make sense for it to be less than 1. Okay, so 1 minus the square root of 2, that has to be less than 0. Right, so we'll put negative there. And because you know how this sine and cosine functions work, you know that it's probably not going to be balancing there. 1 minus 2 cosine x. If it was 1 minus cosine x, maybe it would be a balance because of the way that, think about the graph would work. Okay, but we are going to have sign changes, but maybe you need to be sure about that. So we're going to do pi over 2. F prime of pi over 2 is going to equal... you could have done pi or 3 pi over 2 also. It really doesn't matter. And that's going to be 1 minus 2 times cosine of pi over 2. Well, cosine of pi over 2 is 0, so it's going to be 1, which is a positive number. Okay, and then x equals, you could do 7 pi over 4, something between 5 pi over 3 and 2 pi. I'd like to think you could even do 2 pi because it's going to be defined there, and we're not going to have a sign change earlier. Yeah, either way, you're going to see it's negative, whatever your analysis is. And so I'm going to need to give myself some space here. Oh, I'll have hardly any. But x equals pi over 3 is going to be the location of the local minimum, because f prime went from negative to positive. It's going to be a little noisy here. But x equals 5 pi over 3 is going to be the location of a relative maximum because the derivative f prime went from positive to negative. All right, now that was a really robust set of algebraic problems, and that's, I think, gonna make a good kind of standalone video, so I'm gonna call it for this one, and I'm going to come back and work the rest of the problems on homework 3.1 in a separate video. So that's gonna be all for this video. Thanks for watching.